All right. Hello, everyone. We are getting started today on the fourth probabilistic programming session. This is our last one. Right, so we had PP1, conjugate models, PP2, regression and classification, PP3, variational inference, and today we have Bayesian inference in dynamical models, which we typically call Bayesian filtering and smoothing. And so I mentioned before that this is the first assignment, and then this is this covers the second assignment. So what we're going to do today is, I think you have all the information you need to make the second assignment, but I think what you see today will also be helpful in that regard. I'm just going to talk about the Bayesian filtering and smoothing part for the first half. It's not a very big session until 4:15. And then after the break, or we could use the break as well, but I think we can use the remaining time to help you with the second assignment. If you still have any questions, if you don't know exactly what to do, then we can all go around and help you. All right, so let's get started. The problem that we have for today is that suppose you are contracted to estimate how resistant a building is to shaking. So I know that some of you are from the AIES track, some of you from mechanical, some of you from electrical engineering. Does anyone have any experience with mass spring damper systems? Okay. So mass spring damper system is a linear differential equation. It has a second order derivative, but we can cast this into a first order differential equation in a multivariate form. And this gives rise to what's known as a state space model. You have a vector corresponding to the position of the building, x, and then you have, it's displacement from some center, and then you have x dot, which corresponds to its velocity in the displacement from its center. And both of these are then summarized as a vector z. And if you discretize this continuous time dynamical system, the continuous time differential equation, you will end up with something that has the following form. The next state, the next displacement, and change in displacement is some matrix times the previous displacement and change in displacement plus some noise variable, qk. And then we say that this noise variable is Gaussian distributed with some process noise covariance matrix Q. So think of this process noise as external disturbances, anything that causes the building to evolve in a way that isn't governed by this AZK-1 part. And what you may have noticed from this description is that this is a similar classical description as we had with regression. So do you still remember when I wrote down anyone remember this one? Then we wanted to go from this classical description where we say we have some input, some transformation that gives an output, and it's perturbed by some noise sample. And then we characterize the distribution of these noise samples. But what we want is a probabilistic description. We want to describe the probability distribution of this output variable. And in the regression lecture, we wrote that as that is some Gaussian, or well, so we could absorb that noise instance, and then we could describe the probability of the output given the parameter and the input as a Gaussian distribution with this mean and the variance corresponding to the variance of the measurement noise, of the noise samples that perturb this relationship. So now we are going to, right, so this is for regression models. And now we're going to do the same, let's just do it here, for a state space model. So if I have some zk, which is some a times zk minus 1 plus qk, where qk is some Gaussian distribution centered at 0 with a covariance matrix of q. And so if I want to... So suppose I know this variable. If I know this variable, right, I set this, I know the mass of my building, I know the friction, I know the stiffness of the building. If I know a variable, does it belong in this P description? The probability density function? Yeah, indeed, it doesn't belong in there. It's not a observed variable, it's not a random variable, it's something that is set by us when we construct our model. So it is part of the actual equation, but when we write things in terms of this abstract form, in terms of probability distributions and dependencies, then this A is not a part of the distribution. Any thoughts on what should be here on the right-hand side? I can't reach further than that. Yeah. Yeah. This one. This is the mean. 0 mean, yeah. That's a Q. Capital Q. Yeah. Yeah, that's exactly it. So you can see the A is in the specific parametric specification of this probability distribution, but it's not in there when we talk about these variables in a more abstract, high-level language. So indeed, we're using the same trick to come up to a probabilistic state space model. State space models typically have distinction between states, the position, and potentially more derivatives than just velocity of that particular thing that you're tracking. So for instance, if you're tracking a car, you might want to track its position, velocity, and acceleration. That's not in here. This is just position and velocity. And there are also these models for drones, which also take higher order derivatives, like jerk. And if you want to do model predictive control, you can have a minimum jerk controller, something that tries to minimize the fourth derivative of position. of a drone. But typically, you would build these states with some position and its derivatives, but you don't observe all of the derivatives directly. You are dependent on a sensor. So if you have a camera makes a snapshot at a certain point in time. Then typically a camera makes 24 frames per second, so it makes 24 snapshots in 1 second frame, in 1 second of observing a building, for instance. But a camera only, when it makes a snapshot, you can only see the displacement. You cannot see the velocity of the building as it's shaking. And so you would write that as, you have some measurement matrix, some masking matrix, something that's, well, still part of the state space model. So say you have some measurement with a camera, for instance, with some measurement matrix of the current state. Right, so this thing here is, this thing is position and velocity. So it's x at time k and then the change in x at time k. And we don't observe this one, we only observe the displacement itself. So this measurement matrix will be a 1 and 0, and that maps into our measured value. If you would have something like a radar or an accelerometer, you can sense velocity, you can measure velocity and acceleration directly, and your measurement matrix would look different. So if you have an accelerometer, and this thing would actually be like with the second derivative of position, then this would be 0, 0, 1. And then we are just measuring acceleration. But here, it's fairly straightforward. We're going to assume that we have some sort of snapshot of our of our building as it's shaking. And so our C matrix just is 1 and 0. So I'm going to ask the same question again. So what will be here? What kind of distribution are we looking at here? What are the random variables in this particular equation? Also known as the measurement model. Oh, hold on. Any thoughts? What should I write there? Yeah? Yeah? Yeah, it's a big R, yeah. If my writing is unclear or if my chalk is too thin, please let me know, then we can find a different way of writing it, but it may not be better, but at least I can try a different. Yeah, we're at the end of the board, so that's also not great, but yes, that's exactly it. So to summarize, our probabilistic stasis model is P of zk given zk minus 1 and P of yk given zk. And who here has does someone have a control background, perhaps? Yeah? So if you have been studying control systems a little bit, then your classical equation might have a control, an input. That might be someone like King Kong shaking the building, and then that would translate like this, and you would have a UK here. But for now, we're just going to assume that the building shakes, that there is some force applied initially, and then later on there's nothing that forces the building to shake. Or we could also say that this UK, this input variable, is 0 everywhere over the course of our measurements. That would be the same, saying the same thing. All right, yeah.
So the difference between control systems and this, that you're assuming that every state has some uncertainty?
No, so if you do control with this, then your states also have uncertainty. Depends a bit on do you know your controls? If you know your controls and your control matrix, then your inputs don't add anything to the uncertainty over your states. So the marginal state distribution, so the distribution over the current state Zk, its variance is purely determined by the process noise. But if you are uncertain about your inputs themselves, like you don't know them, you want to infer them, or if you don't know your control matrix, then that could add to your variance term there when you do state estimation. Right. So in the notebook, I have a piece of code where I generated some data that we are going to load in. And I'm giving you the mass, friction, and spring stiffness of this building. So then we have this dictionary data, and this dictionary has a key for M, that's mass, C is friction, and K is stiffness. And then we also have some measurement noise variance, sigma there. We know that our discretization time step, and then if I plot this, you could see something like this. So the red line are the true states of the building as it's being displaced, and then the black dots are our measurements. So you have a camera pointed at it. Could be that there's some computer vision algorithm that detects the displacement of the building, and it might be light or clouds or fog or snow or something that is causing our measurements to deviate from the true state, the true displacement of the building. I don't have any units here. That's because I just generated a system. I wouldn't know exactly what a realistic unit would be for a shaking building. Maybe meters, maybe centimeters. I actually don't know. Okay, so before we move on to this one, so we've converted this classical description of a state space model into a probabilistic state space model. And because we only observe the displacement, this thing is actually scalar in our case. So this R would represent some measurement noise covariance matrix, but we only have, because yk is scalar, we could say, well, actually it's also a scalar noise, so we just have a single sigma squared as our measurement variance. So then we change this to sigma squared. Suppose we want to build a joint distribution over the entire time series. Any idea what still needs to be added to this description before we can describe the joint distribution over all of the states and measurements? So with that I mean, so these are just for specific time points, k, but suppose I want a joint distribution over all of the, well, let's do t for time, over all of the states, over all of the observations and all over the states in time. What still needs to be added? Yeah. Yes. So whenever you do simulations, you always have an initial condition from where you start. We might not know that initial condition exactly, so we would have a prior distribution on our states. So that could be a, oh sorry, I wrote an X, that's supposed to be a Z. So we have some p z0. We don't have measurements of our initial state. But we might say that our initial state is centered on some mean displacement and some, we have some uncertainty about that. And then we can build an entire joint distribution by taking the initial state. We have our state transition at every time step. So we take z0, we calculate the probability of z1 given z0. And then we also have a likelihood or measurement model that says the probability of our y1, our first observation, given our first state, z1. So this description is the joint distribution, the generative model. Let's give it a name. Of our entire time series. That's the full probabilistic model that describes how we think our measurements were generated. Any questions on this? Okay. Yes, so we want to do state estimation, so we don't know these states, we only have these measurements, so that will be, let me turn this one off. Right, so we only have these measurements, and we want to filter them. We don't want these noisy measurements, we want to know the true state of the building's displacement, because then later on we can use that if we have some sort of damper, something that moves in the other direction to counteract the shaking and to prevent the building from falling over, or someone getting their lunch moved over them because the building is moving in that direction. So we're doing filtering. We're trying to remove the measurement noise. We're trying to infer states, also known as state estimation. And we can use our probabilistic programming toolbox for that. I think so. Bert in his lecture describes what the posterior distribution would look like to these Bayesian filtering equations. Go back to the dynamical models lecture. And then we end up with classical Kalman filters. So if you do all of this by a message passing perspective and Bayesian inference, you do end up with the standard Kalman filter equations. We're going to see a little bit later in this lecture that the Kalman filter is actually a special case of a Bayesian filter. You can do much more if you follow this framework. So these are the updated equations, but we're not going to do that by hand. We are going to write a probabilistic model in our probabilistic programming language. So I have here a linear Gaussian dynamical system. It has some prior parameters for the initial state. And then I have A, C, and Q. I assume that these are known. So my mass, my friction, and my stiffness. My measurement matrix and my process noise covariance matrix. And it's sort of unrealistic to assume that we know our process noise and our measurement noise exactly. Typically you would calibrate this, so you would have maybe a two-step estimation procedure where you first try to figure out what the Q is in sigma, and then try to do state estimation. But we're going to see later on that you can also just put a prior on Q, or sigma, and then infer it simultaneously using variational inference. So our prior state, so I've tried to convey this a couple of times over the course of the course, that these probabilistic programming languages are designed to match your math equation as much as possible. So we have an initial state prior, z0. So that's a variable z0 which is distributed as a multivariate normal with these prior parameters that we supply as initial mean and variance. And then we have a for loop from 1 to the length of the time series where we have a state transition, and we say that the kth entries of the state depends on the previous state, and so we have to specify that our zk minus 1 matches z0 at k is 1. We're just going to use this a and q that we had before. We have our observation y. Then we have this dot operation again, because our c is a row vector. C is a column vector, and then z is a vector. I'm trying to do a dot operation. And then we have our sigma squared as our measurement noise variance. Now if you just go through this for loop, then we are building this joint distribution, this generative model. And here we're able to do inference exactly. We're able to infer posterior distributions exactly. So if I just provide all of the necessary information in my model, I provide it with our observations for data. I can ask for free energy as our cost function for how well did we describe our data, what is our precision weighted prediction error, plus the complexity of my model. And yeah, it's fairly fast in how quick it can do filtering, or smoothing in this case, because we are providing all of the data at once, so we're going, all of our state estimates depend on all of the data. So if you extract the means and variances for each of the states, so our posteriors over z, there are going to be a lot of them. There's a 300 element vector of distributions, but each of these elements in this vector represents one of the marginal states, so the distribution of zk at a particular time point k. But I can extract the mean and variance from that, as I'm doing here for this mz and vz. And if I then use this, so I can plot them over time and then use this ribbon command that you've already seen from the assignment to show the uncertainty of my state estimates at every point in time. So then if you use that, you can see here that it follows the distribution somewhat, but you can see it's quite jagged and as in it's not so smooth. Yeah. That's a really good question. So I have a vector. What I want is the mean out of every element in that vector. This is going to, because every mean is a vector, so now I get a vector of vectors, but I don't want a vector of vectors, I want a matrix, an array. And cat essentially allows me to map a vector of vectors to an array. So I can do, it stands for concatenate, so I can do vcat. I need to double check whether I need vcat or hcat for vertical concatenation or horizontal concatenation. Yeah, that's not the one. Yeah, so now I get a matrix. Oh, I get a matrix of vectors. That's not very pretty. That is also not very pretty. Yeah, okay. So what are these three dots, you may ask? I explained this last time before, that you can splat something. So if you have a lot of elements in a list, you can put them together. What's the best way to explain this? So typically, you can't do splat in isolation. It can only work as a function argument. Yeah. So this is going to raise an error. But so essentially, when I say, is it vcat or acat? Yeah. Okay. Essentially, when I call a concatenate function and I first splat my input argument, I'm going to take that vector of vectors. I'm just going to put them all together in a list, and then I want to horizontally concatenate them until I get a particular shape. So you can see that with vcat, it's going to vertically concatenate all of these elements. So I get my two-dimensional vectors, 300 of them, now I get one vector of 600 elements. But if I do the horizontal concatenation, then I get an array of 2 rows and 300 columns. So this is a slightly more advanced use of this splat function inside a concatenation when you're manipulating an array. But if you have some function which is defined with a and b, and you have a list, a comma b, then you can either say, give me f of x1 and x2. That makes sense, right? You're indexing, give me the first entry of x, and that's going to be my first input argument. Give me the second entry of x, that's going to be my second input argument. What you could also do is f splat, then it unpacks the array and just adds them as input arguments to my function. And here what I'm doing in this cat is just a function to concatenate things, is I'm taking this vector of vector and then I'm splatting each of these elements of the vector of vector into a single object, and then I reconstitute, I populate this matrix in a certain way with those elements. I think the best to do is just try it out. I don't want to go into it in more depth. Because we have to move on. But does that answer your question? Yeah, okay. Right, so we have these inferred results, state estimation, but they're not so smooth. They're quite jagged, and ideally what we would like is that if there is a lot of uncertainty, for instance, if you have some outlier, that's quite a big change, right? We remember that we're always making a prediction, and then we are making a weighted average between our prediction and a correction from an observation. And the weights in that weighted average are determined by our variances, because we have these two distributions. But if you have an outlier, if something is just very far away from your prediction, then you have a quite large prediction error. So then ideally what we would like to see is that the uncertainty for my state estimate is quite large, right? So we made a really big prediction error, so we should be really uncertain about where we are at that point in time, where the building is when it's shaking. If you suddenly observe that, it's way out, then you should be very uncertain about your inferred displacement. But we don't see that so much. And this is most likely due because I provided a process noise covariance matrix that was not properly calibrated. So let's see where I define this. So I defined this Q matrix as an identity matrix. It's just once for convenience sake, but it doesn't really represent what happened in my building. My building is not being pushed around on the order of an identity matrix. So we'd like to infer this process noise matrix simultaneously. I'm just going to hide this. So if we look at these equations, let's forget this regression for now. If we don't know Q and we would like to simultaneously infer Q, what do you think we should do with our state space model description? Or maybe we should just use this one. Okay, let me just... What do you think should be added to this, and where do you think it should be added in order to infer Q simultaneously? Yes. So before this bar? Sorry? Okay. Oh, this Q is still here. So here we say that our current state depends on Q. So our current state is a variable that is governed by Q. And so if we have a probability distribution description, so our language in terms of P's, we have this random variable zk, and it depends on Q. Should Q then be on this side or on this side of the bar? Yeah, exactly. Yes, so our current state depends on this Q matrix. In this functional specification, we have a Gaussian distribution with Q as a variance matrix, a covariance matrix. But then because Q is on the right-hand side, so we're using this here on the right-hand side, but we want, so that means that all of our results are going to be dependent on some Q. But if you remember Bayes' rule, let's do it with y's and or x's and thetas. Let's do this. So Bayes' rule, so we have some variable that depends on some other variable. The data depends on parameter. And then we want to know what the distribution is over the parameter. So we actually want to go from x depending on theta to theta depending on x. And in order to do that, we are moving this theta from the right side of the conditioning bar to the left side of the conditioning bar. And then to do that, we need this thing, a prior distribution, a marginal distribution. You can always think of a marginal distribution as something with a bar and then nothing behind it. It doesn't depend on anything. But you always need some distribution, some marginal distribution with that variable, with nothing depending on it, or well, a distribution over that variable. Then you construct the joints. You divide by the evidence, and that gives you the posterior. So if we take that into account in this state space model description so far, we have Q here. We say Q is now a random variable. It's not set by us. So our current states depend on Q. What do I need to add here to make this complete? I mean, this is just bookkeeping. What do I need to add to these three to make the joint distribution complete? Yes. So we need a separate prior for our random variable over the process noise covariance matrix. Now, you haven't seen probability distributions over positive definite matrices before, I think. Correct me if I'm wrong. I'm not sure if Bert treated this. I don't think he has it in here. Oh no, we did have it. We had it in the latent variable model lecture. So if you remember from the mixture model, we described the Gaussian with a prior distribution on the mean and the precision matrix of a component. Here we have we could talk about a precision matrix, so the inverse of Q. Do you remember what that distribution was? It's a probability distribution over a positive definite matrix, which is a really weird thing. that was a Wishart distribution, which we would write like this. Just as with the gamma distribution is a probability distribution over positive values. So you have something here which goes to infinity, this is 0. So it has probability 0 over the negative part, but it has some positive probability over the positive domain. And you can think of a positive definite matrix as some higher dimensional object which has some cone in the positive quadrant of some higher dimensional space. So it's just a probability distribution over that section of some higher dimensional space. And but the Wishart distribution is a generalization of the gamma distribution. And so it has this degrees of freedom parameter, which we will call with some prior n0, and then it has a scale matrix. And the scale matrix is also a positive definite matrix. And the mean of a Wishart distribution is the degrees of freedom times its scale. And the variance of Wishart distribution is a bit more complicated. We don't really need that in the course. It's just a suitable prior distribution for the Gaussian distribution. And why suitable? Because the Gaussian distribution requires its covariance matrix to be a positive definite matrix. This is a probability distribution that assigns 0 probability to any matrix that is not positive definite. So we had a Wishart distribution for precision matrices, but you could say our precision matrix is the inverse of our covariance matrix. And so there also exists something called an inverse Wishart distribution, just as there is a gamma distribution and an inverse gamma distribution. Gamma distribution for precision parameters, and inverse gamma distribution for variance parameters. So we are going to put a prior over this Q that is distributed as an inverse Wishart distribution with some prior degrees of freedom and prior scale matrix. And then if we take our generative model, we add this Q. So now when we start adding all of these things together, previously if you start at K as 0, then you have P of 0 depending on P Z0. And so that means that Z0 would be behind the conditioning bar, and so we would depend on something where we don't have a prior for, so we had to add a prior. Now our PZ1 also depends on Q, so we have to add a prior for Q. But if we multiply all of these distributions together, then all these y's from k is 1 to t, and all these c's from k is 1 to t, and the q, they all appear on the left side of a conditioning bar, so we have this joint distribution which does not depend on anything. That's our new generative model. So now we don't have to calibrate Q in advance. We can just say we're going to infer it simultaneously. A bit like what we do in the second probabilistic programming assignment. Yeah.
So we do in the toolbox, is it then that we specify the separate distributions and then the toolbox is all that generative model?
Yes. So in the toolbox, we describe these things. Then we have a for loop because we describe them for every for every k from 1 to t. So the toolbox essentially takes this. These are all of the factors of my generative model. And from there it can construct a joint distribution, construct posteriors and approximate posteriors. But the main point of this toolbox is that if you have a probabilistic model, if you're designing a probabilistic model for a particular problem, right here we're thinking of these shaking buildings, and we want to design a probabilistic model to do state estimation and process noise covariance matrix estimation, you only have to come up with a reasonable specification of what random variables depend on what else. What random variables depend on each other, what data depends on which random variables. That's your model structure, your model specification. That's the only thing you need. You feed that to the model, to the toolbox, and then it takes it from there. So that gives us what I wrote down here. If you look at the model specification, it's actually exactly the same as before. We just see that there's an additional line here, right? So if you want to simultaneously infer the noise covariance matrix, you can add a single line here. Q is distributed as an inverse Wishart distribution with these two prior parameters. Q is still just part of it here. And then the model knows, so I've called this linear Gaussian dynamical system Q, and the model knows that, okay, so Q is an unknown variable, all of the states are unknown variables, and I'm going to try to infer them simultaneously. I have an exercise here to think about. Let's do a break anyway, then you can think about this exercise. Should the prior parameters be high or low for this Wishart distribution? And after the break, I'll quickly just follow up on the result that's going to come out. And then we'll talk about the second assignment. All right? So let's meet up again at 4:30.